So last time, if you remember, we looked at some acid-base reactions, and we talked about the definitions of acids and bases being this: that acids donate H+, bases accept H+, and that we remember that this acid-base designation has to do with what they're doing in a reaction. It's not an inherent quality of a molecule. It's in this reaction, this thing is an acid, in this reaction, this thing is a base. So we talked a little bit about conjugate acids and conjugate bases as being having lost or gained hydrogen. And then I also mentioned that the main mistake that people make in this is forgetting about the charge. So it's easy to just stick an H on here or take an H away here. What people forget about is that it's not just H, it's H+, it's a hydrogen ion. So it's going to change the charge. If you add H+, your charge is going to get more positive or more or less negative by 1. And if you take H+ away, then your charge is going to get more negative or less positive. So in these examples, we were looking for, oops, that's not correct, conjugate acids oh no, that's right. We looked at the conjugate base of NH4+, so we're saying, all right, what kind of a base can get H+ to become ammonium, NH4+? And you found that it's NH3. A neutral NH3 molecule plus NH+ is going to end up being an NH4+. We can do the same thing with a negatively charged ion like cyanide. Cyanide negatively charged, you add in the H+, and you end up with the neutral HCN. So it goes from negative to neutral because it's gained a positive there. All right, so let's try another one. Some molecules, and we saw some of these, are known as amphoteric, which means that they can act as an acid or a base. So you have to look at the reaction and determine which one they're acting as. And one way you can do that is by thinking about the conjugate acids and the conjugate bases. So one example of an amphoteric molecule is bicarbonate ion, or hydrogen carbonate. So this molecule has both a conjugate acid from when it acts as a base and a conjugate base from when it acts as an acid. So let's find those. See if you can write the conjugate acid of HCO3- and the conjugate base of HCO3-. So what'd you come up with for a conjugate acid for HCO3-? How'd you figure that out?
H2CO3.
Right. So we add the H+ and get H2CO3. Right, so it's gone from negative to neutral, and it's gained a hydrogen. This is called carbonic acid. So then what's the conjugate base? What happens if you do the opposite? CO3? Not sure about the rest. What do you think? Is that what you're thinking too? So everybody says CO3? CO3, but what about the charge? Is it neutral then? If you start with a negatively charged HCO3 minus, and then you take out a positive, what's the charge on the CO3? Still negative, but more. 2 minus now. So you see the trend here? You take away a hydrogen, you go from neutral to 1 minus, then 1 minus to 2 minus, as you take away those H pluses. We also know what that ion is, right? What is that? What's that ion called? Yeah, that's carbonate. So we've got carbonate, bicarbonate, carbonic acid, depending on how many hydrogens are there.
So you're just subtracting the hydrogen from the base.
Right, to make the base. And we're just saying like if it got a hydrogen from an acid of some sort, that's what it would be. If it gave up a hydrogen to a base, this is what it would be. Or yeah, there'd have to be something in a reaction that actually takes that thing. So we can also talk about these relationships in terms of in between these things. So H2CO3 is the conjugate acid of HCO3, but HCO3 is actually the conjugate acid of carbonate, right? Because carbonate plus an H plus gets you this. So this is the conjugate acid of this. Similarly, this is the conjugate base of this. This is the conjugate base of this. Right? So we add or subtract those H pluses, and we get the conjugate acids or bases. All right. So ready for a little bit of math? Totally? Pretty excited about it? Okay. Now this is math I'm going to show you more than you need to do, but I'll let you know the part that you need to do.
Is this going to be like showing us on an exam, but then like we're surprised we have to actually do it?
No. If you're surprised, it's, well, there shouldn't be things that are surprising with everything listed on Blackboard and all the problems and everything. So this is kind of a weird thing, but it's real. Water does not exist as just water. This is not like some kind of weird metaphysical argument, but there's a chemical thing that happens in pure water. Pure water is not just individual H2O molecules. Water actually breaks apart a little bit by itself in this kind of a reaction. So this is a really strange kind of acid-base reaction. Which molecule on the left is acting as an acid? It's a trick question. They're the same, so it could be either one. So we'll call this one the acid and this one the base. But going from right to left, we can definitely say that one of them is being the acid and one of them is being the base, right? Which one's being the acid? Right, hydronium. Okay. No, I meant on this side, so they're the same. So yeah. So we could really just also say it the other way, just so we don't get too confused here. All right, so in water, water molecules are actually reacting with each other as acids and bases. Some hydrogen is getting transferred from some water molecules to some other water molecules. And the way that we talk about this is by looking at the concentrations of these species. And we're going to use these little brackets to indicate that. A bird. One of my students yesterday had to call the facilities because there was a mouse running around on the 3rd floor. It's like a pretty good sized one. It was pretty friendly. It was coming up and like sniffing people's shoes. Yeah. That was a mouse. It was about tails. Yeah.
Or like, long disgusting tails.
Yeah, rats have the like big like
Yeah, I know,
bear
rats.
tails. Yeah. It was large. I mean, it was large for a mouse, but it was definitely a
How
mouse.
big was that?
It was running around the hallway, that back hallway by the lab.
Did someone let out like from like the, by that zoology,
Oh, I don't know.
lab, where they have like.
Maybe.
Like,
It was black, like a dark gray or black. Is that the color of those in there? I don't know.
what? I don't know.
I don't know.
I'm pretty sure dark gray mouse would be.
It's so. It's so.
What's the difference between that color mouse, that color size of the mouse versus the baby rat? It's gray.
The tail. You can definitely tell the tail on a rat. And just the shape of the body. My sister always had pet rats when we were growing up. So
Oh my god, ew.
they're very friendly.
You're disgusting.
It's like Chicago rats and different babies.
Right. So anyway, I don't know how we got that, but so this is the hydrogen. We're going to call, when we put brackets in this, we're going to call this the concentration, usually in molarity. Whatever the concentration is in the solution, and then of course, we also talk about the hydroxide. So in any water solution, you're going to have a certain amount of hydronium ion concentration and hydroxide ion concentration. In pure water, what do you think? What do you think is going to have more or less of them? Do you think one's going to be more than the other, or you think it's going to be even?
Like water to water, like
Yeah.
tap water versus distilled
No,
water?
just pure water. Nothing else in it at all. Distilled water. It's going to be even, right? So we'll say in pure water. So in pure water, the hydronium ion concentration equals the hydroxide concentration. And then here's how we get some information about acids and bases. In acids, so now we're not talking about the kind of theoretical, what is an acid reaction, what is a base? We're talking about an actual sample of acid. So a jar of acid, a beaker of acid, the hydronium concentration is greater than the hydroxide concentration. Makes sense, right? If acids are molecules that give up hydrogen, and you put that molecule in water, it's going to give up H plus to the water and make more hydronium ion. We saw a reaction like this before. It was our first reaction, I think. Okay, second reaction. If you put HCl in water, you make hydronium ion. So if you're making more hydronium ion, you're making something more acidic. And so the stronger the acid is, the more hydronium ion is there. So then in bases, it's just the opposite. In bases, the hydronium ion concentration is less than the hydroxide ion concentration. Now, most bases that we talk about are hydroxide salts, sodium hydroxide, calcium hydroxide, lithium hydroxide. So if you put a hydroxide something into water, of course there's going to be more hydroxide in there. So that's where that comes from. Even bases that don't have hydroxides in them, like ammonia, when they react with water, they form that hydroxide, and so they're, is that annoying? Yeah, now you're noticing it. So they're forming more hydroxide and making this. So we measure this. Anybody know how we measure this? What the quantity is called that measures this amount of concentration? Yeah. Right. So this is where pH comes from. And here's the big equation that you do need to know. pH is the negative log of the hydrogen ion concentration. Now log, if you haven't had a lot of experience with that, it's a button on your calculator. Calculate logs using that. But what it really means is the exponent. So these concentrations are small. In neutral water, these concentrations are on the order of 10 to the minus 7. That's a really small number, right? That means,
Is that 1.0?
yeah, 1.0 times 10 to the minus 7. So just 10 to the minus 7. So that is, if we want to write that out, that number. And that's in molar. So 0.000001 molar is how much hydrogen ion concentration is in pure water. What that tells us is, if we look at this reaction, it's not really making a lot of this. Most of it is just staying around as regular water, as H2O. But a little bit is becoming H3O plus, and that little bit is that much. So that's how much is becoming that. So you got a really small number. And just like with moles or with other things that we've dealt with in this class, whenever we have really big or really small numbers, it's kind of annoying to have to worry about the scientific notation all the time. It's annoying to have to write numbers that look like that, or even more zeros if they become even smaller. So we come up with a way to kind of abbreviate that. What happens when you take the log of something is you get the exponent. So the log of 10 to the minus 7 equals minus 7. Basically means take away the base part and just leave the exponent. So then the negative log of 10 to the minus 7 is the opposite sign. So negative means you switch the sign. So negative negative 7 is just 7. So now we go from having these crazy small numbers to just 7, a totally reasonable integer. And that's where the pH scale comes from. The pH then is a measurement of the hydrogen ion concentration. All right. So where do we get some of these other numbers? Let's say we have a solution. A solution of HCl is going to have a greater hydrogen ion concentration, right? Let's say it's, just for fun, we're just going to make up a number, 1.0 times 10 to the negative 2 molar for the hydronium ion concentration. This is your paper up here? That's all?
Yeah.
So let's just say that some solution of HCl has a hydrogen ion concentration of 1 times 10 to the minus 2 molar. Is this a larger or smaller number than this, than 10 to the minus 7? It's larger. It's much larger. So if we actually write that out, it's 0.01. 0.01 is a way larger number than 0.000001. Million times larger. Or thereabouts. So that means a lot more hydrogen ion concentration, and that's reflected in the pH. So what is the pH then of this?
Would it be 0.0?
You know, that's a regular scale.
Let's do the equation again. So we're going to take the negative log of 10 to the minus 2, which is 2. So the pH of this solution with this hydrogen ion concentration is 2. 2 is less than 7, but it refers to a larger concentration because of the negative. We're switching the sign. So even though we've got a smaller number for the pH, we're referring to a larger concentration. So things lower on that pH scale are going to be more acidic. Things higher up on the pH scale are going to be less acidic or more basic.
The 7 that you had logged, 10 to the -7, was 7 just like a random number?
That was not a random number. In pure water, the hydrogen ion concentration is 10 to the -7.
Alright, but like the pH formula is log to whatever power. negative.
Yeah, whatever your hydrogen ion concentration is, which isn't always a nice even number, but whatever it is, you take the log of it and then you flip the sign. If it's not a nice number, like just 10 to the -2, if it's 2.465 times 10 to the -3, then you're going to need to use the calculator with the log in it to solve that. I think if you got your phone, I don't know if there's a log right on the main calculator.
Yeah.
Is there? Okay, good. Mine isn't, but if I turn it sideways, then it shows up. So you might try that. Yours doesn't do that. Anyway, or just bring a calculator because we use them all the time anyway. Okay, so we talked about calculating pH. So now let's look kind of generally at the scale. The scale goes from, so in pure water, these things are both at this particular concentration, 10 to the -7. So that means if you have the most water you can possibly have, the most hydronium you can possibly have is going to be pretty much 0 in water. And the highest number is going to be 14. Now there are some exceptions for other types of solutions, but in water this is what we're going to see. So pH is generally going to range from 14 to 0. 0, the low end, that's things that are strongly acidic. And 14, the high end, that's things that are strongly basic. So your book has some various examples of things that fall along this scale. Water is right in the middle at 7. So pure water has a pH of 7. Tap water, or drinking water, is a little bit above 7. Things that are really basic, like ammonia or bleach, cleaning materials, are up here. Things like lemon juice, vinegar, stomach acid. So vinegar is 2.8. Coke is 3. So that's very, very acidic also, phosphoric acid. Milk is a little bit acidic. Blood is about neutral. So anything between about 6 and 8 we call neutral. Below 6 we call acidic. Above 8 we call basic in general. And something we'll see in lab on Monday is we'll go into lab and we'll actually measure the pH in various ways. We can use something called pH paper to determine the pH by color, by comparing colors. We can use something called a pH meter, which will actually measure the hydrogen ion concentration and then report it as a number. And we can use something called litmus paper. Have you ever heard of litmus paper? Which is the kind of the crudest measurement. Litmus paper only has 2 colors. It can be blue or red. And so if it's basic, it's blue. If it's acidic, it's red. So it kind of tells you where it is on the scale, or it tells you which side of the scale it's on. It doesn't really give you more information than that. And then since we just had a Halloween, I like to look at this chart also. Yeah. Mm-hmm.
How do you calculate it with the log? Is it like you give a question with like 10 to the minus 2, you are looking for the 2, or like you get from 2 to 10 to minus 2? How do you calculate it?
So if you take a log of a number with an exponent, with a power up there, then the log is the power, the whole power, negative, positive, whatever it is, whatever's up there on the side of the 10,
Yeah.
that's what you take when you take the log. So if you take the log of a more complicated number, like 2.3 times 10 to the minus 7 or something like that, you can type that number out in a calculator and then push log is usually how it works. You push the log afterwards. If you have a graphing calculator or a little bit fancier calculator, then you do the log first and then you put the number in parentheses. So it kind of depends on the calculator that you've got.
No, it sounds like pH minus log minus 2. Just minus 2, right?
Where?
Right. pH minus log.
Yeah, so the pH is not just the log, it's the negative log. Whoops. So you have to invert whatever the sign is on the actual exponent. Yeah, or just flip the sign at the end. Yeah, so you put negative first or just flip it at the end.
Oh.
Because if you just do the log of 10 to the minus 2, you're going to get minus 2. So the pH is the negative log, so you have to flip the sign. Go from negative to positive. Yeah.
Is that number, did you put that on the actual pH scale to minus 2?
You would put, no, the pH scale is in positive numbers.
Okay, let's take it.
So it would go from 0 to 14 positive numbers. You can have negative pH in some situations, but we won't really see that. Right. And you can do it the other way around too. You can calculate the hydrogen ion concentration from the pH. Now to do that, you have to actually raise it to a power. So log gives you the exponent. If you want to go from the pH, you can say, so if you want to calculate the hydrogen ion concentration from the pH, it would be 10 to the negative pH. So whatever the pH is, you raise 10 to the negative of that. So if the pH is 3, then the hydrogen ion concentration is 10 to the minus 3. pH is 6.5, it's 10 to the minus 6.5, which comes out as a different number. All right, so one thing I always think is interesting, especially around Halloween, is looking at the pH of candy. So here are some different candies. You know, the dentists always tell you, don't eat candy, it's bad for your teeth.
Warheads
How
are.
old is this chart?
Oh my God,
I
warheads.
had warheads like recently and was not as sour as it was when I was a kid.
Same here. I was
Maybe they're toning it
really-
down.
Really
This is
disappointed.
only a
Me
year or
too.
so, a year or two old, so it might have been even worse back then. I don't know. Maybe you're just,
I remember like
Less-
almost like coughing and like dying.
Yeah.
I remember
I remember
like
that too.
dry heaving because it was so sour in like the 5th grade.
yeah.
Now it's like, what?
Maybe you just have some desensitized taste buds from all the eating.
Older.
But anyway, the reason that this kind of stuff is bad for your teeth, it's actually two things going on at the same time. Once you get below pH 4, your teeth start to decalcify, so the enamel around your teeth starts breaking down. It can't survive that acidic environment. The acid is eating it away. And that actually isn't that big of a deal. I mean, it's not good, but your teeth can repair that. It can kind of, your saliva neutralizes it and then it's okay. But the problem with that is when you're below that pH, it means that there are basically holes in your enamel that sugar can get into and bacteria can start metabolizing that sugar and eating up your teeth. So candy is kind of the worst. If it's just sour, it's not quite so bad. But if it's sour and it has sugar in it, that's what really starts to decay your teeth. And so you can see that teeth start to decalcify about 4. We already said that soda gets you to pH about 3. So that's why soda is really bad for your teeth. Although, as long as you just drink it kind of in one sitting with your meal or something, it's okay. What you want to avoid is sipping on it over a long period of time. Same thing with coffee, especially coffee with things like excuse me, sugar or sweeteners or syrups, that kind of stuff in it. It's okay to just eat, but you don't want to leave it in your mouth for a while. So you see some of these candies, these sour candies, really get pretty extreme, down to the same pH level as battery acid down at the bottom here.
That's terrible.
Yeah. So, enjoy your warheads. I don't think the actual warheads are on this.
That's sour spray. What
Yeah.
the hell is that?
That's not even.
I don't know.
Like
Must be some kind of a
Chemicals
spray.
in a little spray bottle.
Right.
Let's put a candy label
Not
on
even
it.
sour.
It's mostly citric acid, is what citric acid and ascorbic acid, which is vitamin C. That's what they use to
Chemicals.
make them sour. So yeah. All right, so that's pH. What is the major acid in your stomach? Do you know? Gastric acid. What? Yeah, it's HCl. It's hydrochloric acid is the main stomach acid, and so your stomach's pH is right around 2.
Is that what you, because I was sick yesterday, do you throw that up? Is that considered bile? Is HCl?
Bile is different. In fact, bile can neutralize stomach acid, and that's what it's used for in the intestines. It prevents stomach acid from damaging the intestine. But when you throw up, it's primarily stomach acid, which is why it burns your throat.
Yeah.
And, yeah.
So that's not HCl?
It is. Yeah.
Oh, okay.
But it's not bile. Bile is different.
Oh.
Sometimes bile comes up also, but bile is not HCl.
What color is HCl? Is it
It's like
clear?
red, pink. Gross. Yeah. Yeah, I think we've all probably tasted or had that experience at some point, right? It's not pleasant. If you throw up a lot, you can really damage your teeth in the same way, and your throat and everything else. If you have chronic reflux. Yep. Right. Right. And with a disease called esophageal reflux, where you constantly have that stuff coming up
That is
into your
a
mouth.
legitimate thing. My best friend has.
Yeah.
She had to have surgery.
Yep.
Esophageal.
Reflux. It means that the sphincters, which are these little muscles that separate your esophagus from your stomach, aren't closing properly, and so stomach acid is getting up into your esophagus. Yeah.
She described it. I thought it was.
You're a supportive friend. So anyway, that's some acids in your body. So acids are important in your body. That's how we digest our food. The acid helps break stuff down. It helps prevent certain types of bacteria from getting into our system. But we don't want those to get in places that we don't want them to get in, like in our teeth. So one thing that we will do, well, we can talk a little bit about this in a minute, but first let's define we'll just leave it here because there's room. One common misconception, a totally reasonable misconception, is what we mean when we talk about strong versus weak with respect to acids and bases. Since we experience acids and bases in our lives generally, we kind of have a sense of what this means. When we think of a strong acid, we think of like acid eating through a floor or something like that, or an acid burning your hand really, really badly. But when we use the term strong acid in a chemical context, that's not what we're talking about. This actually refers to whether or not that acid is a strong or a weak electrolyte. So some acids break up into ions and form lots of ions. Other acids mostly stay together. The ones that break up completely are called strong acids. The ones that mostly stay together are called weak acids. So it does not, and this is the big, not corrosiveness, that is how much it burns your skin, not corrosiveness, danger, etc. It doesn't apply to those things when we talk about strong or weak acids in a chemical context. Just as an example, well, so the list, there's a list of strong acids. There's only 6 of them. I'll put them here. You know, I don't think you have to know all of these, but you should know a couple of the more common ones. Hydrochloric acid, nitric acid, sulfuric acid, hydrobromic acid, hydroiodic acid, and perchloric acid. Those are all the strong acids by this definition. And what does that mean? They dissociate, which means break up into ions. Completely in water. So that means that none of them is any stronger than any other one because they all break up completely in water. So if you have 1 molar HCl and you put that or you have 1 mole of HCl and you put that in a liter of water, then you have 1 molar HCl, which has a pH of 0, because 10 to the 0 is 1. Same with any of these other ones. So they break up completely in the water, therefore they're strong acids, and they're all just as strong as any other one. But that doesn't mean that they're the most dangerous acids necessarily. Something like HCl, you know, it's stomach acid. It can be corrosive at high concentrations, but very dilute HCl is not really going to hurt you. Not really going to be a problem. And then every other acid that you can think of, and ones that you can't think of, that we're going to see anyway, is considered a weak acid. So things like HF, hydrofluoric acid, acetic acid, various other ones that we'll encounter, those would be considered weak acids. Now those acids, and the 2 that I listed here, those are actually extremely dangerous materials. Hydrofluoric acid, HF, will eat through ground, it will eat through brick, it will eat through glass, it will eat multiple stories down in a building.
Is that what was in Breaking Bad?
Yes, it will dissolve an entire body. It will eat through a bathtub. And
But
the only
it won't
thing
eat through plastic.
right, it's actually not, it won't react with plastic, it won't react with metal, with stainless steel. So you have to keep HF in either plastic or stainless steel. But it is, so this is really, really nasty stuff, but it's still classified as a weak acid because it doesn't break up completely in water. So it has nothing to do with how reactive or dangerous it is. It's just what its behavior is in water. And sometimes this is concentration dependent. So the next acid I listed is acetic acid. Now acetic acid at low concentrations is just vinegar, so not really dangerous. But at high concentrations, concentrated acetic acid is very dangerous. It, if you breathe in the vapors of it, it can really seriously damage your lungs. So these really have, and these kind of effects have to do with how they react and less to do with the fact that they're acids, especially in the case of HF. It's really more the fluorine that's causing the damage than the acidic part, the hydrogen part. So please remember, when this comes up again, strong versus weak acids. Strong acids dissociate completely in water, form ions, lots of ions in water. Doesn't mean that they are more or less dangerous. Doesn't apply to that. All right. So now let's look at do you want to talk about titrations? No, we'll leave that for lab on Monday. Let's talk about buffers. What are buffers? What?
When you say strong acid, does it have anything, any relation with, electrolytes?
Yes, exactly. So strong acid means it's a strong electrolyte. That's where the word strong comes from. But it sounds, that's why it's confusing, because it sounds like it's strong, dangerous wise. But it refers to its electrolyte behavior. We should also mention, we didn't say anything about bases here, but same idea. A strong base is one that dissociates completely in water, breaks apart. Sodium hydroxide is an example of that. Sodium hydroxide, when you put that in water, it's all sodium ions and hydroxide ions, and there's no sodium hydroxide together left anymore. But some other bases like ammonia do not break apart completely. So those are considered weak bases. And again, not a measure of how dangerous or corrosive it is, just a measure of how it forms ions, how it forms electrolytes in solution. All right, so buffers. What are buffers?
Yeah, that was good.
Everybody kind of does the same motion.
What else is that?
Yeah, so it's a little, what?
Because everybody's doing this, I'm saying it correctly.
Oh yeah, right, yeah. Okay. So yeah, buffers are solutions that resist a change in pH. So let me show you what this might look like. Okay. So let's say we have some water. What's the pH of water? Just pure water. 7? Yep, 7. Okay. Let's put in a few drops of HCl. Just a few drops. So now we've got some H2O and some HCl in there. That pH drops dramatically. And we'll see this on, depending on how strong the HCl is and how many I mean by a few, but that pH is going to drop to like 1 or 0. Fast. A couple drops and it's gone. Similarly, if we add a few drops of a base like sodium hydroxide, a strong base, that pH shoots up immediately to like 13, 14. All right, so pure water, neutral things in general like this, pure substances like this, don't resist a change in pH. They just change. You put a little bit of acid in, suddenly it's all acid. You put a little base in, suddenly it's all basic. Buffers have a slightly different behavior. Let's see, I guess we'll just do it over on the side here. So let's say instead now, use a different color, we have a buffer. And that buffer can still be at pH 7. In fact, you can make a buffer at whatever pH you want. Let's say we made a buffer at pH 7. And we do the same thing. A few drops of HCl. A few drops of sodium hydroxide. So now we have buffer plus sodium hydroxide, and that pH, or whoops, is it HCl? That pH is still 7. And in fact, you can put quite a few drops of HCl in there, and it will resist that change. In fact, if you measure it down carefully enough, you'll notice the pH is changing very, very slightly. You put enough HCl there, yeah, then it's going to start going down. It's going to start dropping down. But for a while, drop after drop after drop, there's no change in the pH. And the same thing happens with base. So you put a certain amount of base in, pH stays the same. Again, it changes a little bit. So if it's 7.0, the few drops of HCl might move it to 6.9. A few drops of NaOH might move it to 7.1. But it's essentially the same. And that's what a buffer is. So the way a buffer works is by taking advantage of the reactions, the neutralization reactions with weak acids. So a buffer is made out of a weak acid and its conjugate base. Like, let's say acetic acid. So I'm going to take this much acetic acid, which is HC2H3O2. And then I'm going to put an equal amount of its conjugate base in with it. What's the conjugate base of acetic acid? If acetic acid is HC2H3O2, what would its conjugate base be? Yeah. It's all this stuff without the H. And then what about the charge? Right. So it's going to be -1 because we took that H plus out. That ion is called acetate. So we've got acetic acid and its conjugate base in like equal amounts. This is how we make our buffer. So let's look at what happens when we add some kind of acid. Some kind of acid that gives H plus, whatever it is, HCl or something. When we do that, that extra H plus hooks up with the acetate and forms more of this. So we add some H plus, we now have more of this and the same amount of this that we started with. But notice what happened there. It didn't affect the overall hydronium concentration, that H3O plus. So this acetate kind of acted like a sponge and soaked up that extra hydrogen so that it didn't go into solution. Because acetic acid is a weak base, it doesn't break back up again, at least not very much. And so it's able to kind of absorb or soak in this H plus like a sink, pulling it out. And if it's not in the solution, then it's not affecting the pH. It's not affecting the acidity. We go the other direction. Something similar happens. If we add a strong base, like hydroxide, we're going to pull that hydrogen off of the acetic acid that's in there. So now we're going to have less acetic acid and more acetate, but again, it doesn't affect the overall solution. It's not messing with the water molecules in solution, and so it's not affecting the pH. Now, as you can see, at some point, you're going to run out of sponge or whatever, and we're going to run out of molecules, and now it's going to start affecting the pH again. But as long as that buffer is in there, you're going to be able to control small changes in the pH one direction or the other. And this is really important in biologically, because our bodies actually are very sensitive to pH. Anybody know what normal blood pH is? Yeah. The normal blood pH, it's reported here, but as 7.35 to 7.45. That's a pretty narrow range. Yeah, so around 7.4. That's a pretty narrow range. And if it gets much lower than that, yeah, cells just start to die. They just can't function. If it gets much more basic than that, same thing. So you're talking about not a whole lot of room for error here. If your blood weren't able to buffer itself, if it weren't able to control for those changes in pH, you'd be in a lot of trouble because all kinds of acidic stuff gets in your blood and whatever, right? Yeah. So let's talk a little bit about the acid-base reactions that happen in blood. What's the major source of acid in your blood? You know, what causes your blood to get acidic? Yeah. So carbon dioxide, which is a waste product of respiration, right? You eat stuff, the stuff you eat becomes carbon dioxide. So carbon dioxide gas dissolves in the water in your blood to form carbonic acid. Now it's a weak acid, but it does start to break apart. So carbonic acid in your blood reacts with water when it dissolves to form bicarbonate and hydronium. And so there's the source of acid. So that carbon dioxide is making your blood acidic. That's why it's a waste product. Carbon dioxide is something we have to get rid of. How do we get rid of it? Yeah, through our lungs. Comes out and we breathe it out. So depending on what's going on in your blood, because these are in equilibrium, meaning they go back and forth, you could end up having more or less than you actually need, more or less acid than you actually need. And the carbonate itself actually in the bicarbonate acts as a buffer. Remember, this is a weak acid. So having carbonic acid and carbonate in your blood is acting as a buffer. But if you disturb that too much, you can cause some problems. So what are some ways that you can disturb that? You know? Hyperventilation. What happens when you hyperventilate? It's the opposite, actually. If you hyperventilate, you're blowing out too much CO2. So when everybody know what hyperventilating means? It means you're breathing really hard, like, you know, because you're scared or whatever. So when that happens, or you have some real problems, medical problem that is causing that. So when you're breathing really hard, you're expelling too much CO2. Too much CO2 is going out, and not enough is getting into your blood. If the CO2 is what's making it acidic, then what's going to happen to your blood pH if you're blowing too much CO2 out? Is it going to go down or up? It goes up, so it's going to become basic. If you're blowing out too much of the stuff that makes your blood acidic, then your blood's going to become too basic. And that's called alkalosis. Blood too basic. high pH. So you're blowing off your CO2, not enough of it is getting into your blood, and it's causing your blood pH to rise. It's called alkalosis. We haven't really talked about this, but another name for bases are alkalins. So if you hear the term alkaline, that's talking about a base. Something could be acid, something could be acidic, or alkaline is another way of saying that, rather than basic. So alkalosis is your blood too basic. The opposite of that then is acidosis, which is when your blood is too acidic. Now there are a few different causes of this. There's a whole table of it in your book, and you can look this stuff up. This can be respiratory, like we're talking about, where it has to do with your CO2, whether too much of it is leaving or too much of it is staying, not enough of it is leaving. Can also be metabolic, just meaning that the reactions going on in your blood are causing too much hydrogen, so different sources. So if you are hyperventilating and your blood is going into alkalosis, what do? How do you stop that CO2 from leaving so much?
You have to slow your breathing down. Breathe in through your nose,
Right.
out through your mouth.
Right. Right. So you got to slow your breathing down, stop doing that, breathe in a paper bag.
Most likely you have like high blood pressure too.
Yeah. And in fact, the paper bag thing, there's some argument as to whether it actually makes you breathe more CO2 or if it just makes you kind of slow down and focus on your breathing because you've got this big paper bag now. But either way, that's the effect. And the book has this great picture of it. I have to show you because it's terrible. But, well,
Oh, I
did you see it? It doesn't look like somebody hyperventilating. Yeah, it just looks like. That's okay because we're gonna look at some problems in the book here anyway. But when I see this, if I saw this picture without context, I would not immediately think, oh, this person is hyperventilating. I would think this person is having a good Halloween. All right, so this is how a question is asked about this. And let's see. You still see it if I turn this light off? Yeah. Whoa. So here's how the book answers for trauma. A person can start to hyperventilate. To avoid fainting, a person might breathe into a paper bag. To avoid fainting. Why did I say that twice? Luckily, they just revised this for the 12th time, so good thing they didn't catch it again. What changes occur in the blood pH during hyperventilation? So we talked about that. Right? But if I were to ask you this question, how would you answer it chemically in terms of what's going on? So how would you answer a question? What exactly is going on in the blood causing hyperventilation? Or because of hyperventilation, causing a change in the blood pH?
We add more base, so we can lower it down the amount of pH.
Well, lowering the pH would be making it more acidic.
You want to know what's happening to the blood during hyperventilation?
Yeah.
I'm not too sure, but I'm thinking you're trying to control your breathing by breathing through the paper bag in the sense that the air is not on every place. So
Right.
it's breathing here.
But how is that affecting the blood? What's happening at the molecular level is affecting the pH.
You're inhaling the gas that's
What gas?
causing CO2.
Okay.
You're
So
inhaling
what's that doing in
CO2.
your blood?
That's oxygenizing your blood.
The CO2 is oxygenizing your blood? Or the
No.
oxygen? You're right. So the CO2
That you're
is
focusing
getting
on
in your
breathing.
blood.
You're
What
getting
happens
the
when
right
CO2
amount.
gets in your blood?
It will factor in the whole alkalosis.
It makes it more acidic, right?
Right. The CO2 makes your blood more acidic. So if you're hyperventilating, What's happening?
You have too much.
The blood is too,
How did your blood get too basic from hyperventilating?
it's running too much. You gotta chill out.
Well, but I know that, but I mean, like chemically, why is your blood changing its pH?
You're just breathing. You're just getting rid of all
Oh, I'm about to run out of batteries here. Right, so you're in hyperventilating, you're exhaling or expelling too much CO2, so your blood doesn't have enough CO2 in it to maintain its pH. The blood is going to go up in pH. And then the second part of that, which I think you kind of answered, how does breathing into the paper bag help return blood pH to normal? It forces you to take more CO2 in, get more CO2 into your bloodstream. Getting more CO2 into your blood is going to lead to a lower pH. Lower pH.
All I can think about is that YouTube thing where it's like, basic, calling on you basic bitch.
Oh, yeah. So, bueno, pero, que tú dices que eres muy, very basic.
All right. So let's take a look at this one.
So,
So here are a couple good exercises that we can look at. We're going to determine the pH for the following solutions. Save this before my computer shuts off. Determine the pH for the following solutions, and then we're going to identify them as either acidic, basic, or neutral.
Is C just 1 or 0?
It's neither. Sorry. But so let's do A together. A is different, right? Because normally we're looking in the examples we've done together, we've been looking at the hydrogen ion concentration. But in this case, what are we looking at instead? In part A. It didn't tell us the hydrogen ion concentration. So how do we find it from the hydroxide ion concentration? Yeah, it's a little tricky. So I gotta move to the board because my computer is dying. So the hydroxide ion concentration times the hydronium ion concentration always equals 10 to the minus 14. So whatever is up on that exponent, you just divide that number.
So you do.
Yeah, so you divide 10 to the minus 14 by one of these to get the other one.
Minus 14, it's minus 7.
minus 7.
Right, so to find the hydrogen